Now the third case. First we dealt with a line, then a plane. Now we are bending the plane into a sphere. So sphere has three regions that we need to concentrate on. One is inside, on and outside, similar to a gravitational force. Now the derivation can start something like this. Consider a thin spherical shell of charge of radius r and uniform surface density sigma. Now the Gaussian surface. Gaussian surface, what is the pattern? Pattern of electrical field, that is, obviously it is radiating outward as if we have a unit charge. And what should be the sphere then? Spherical. It should be commonsensical to you guys now. So electrical field line generated by a uniformly charged spherical shell is going to be radiating outward from a shell's surface. It's always perpendicular to the surface. We have done all of this theory part, so you should be able to apply it now. Thus, we use a Gaussian surface of radius small r in the form of a concentric sphere with the spherical shell. That is, they share the same correct center. If this is your sphere, with respect to this, we have the Gaussian surface. This being the center, and we have the Gaussian surface. Again, you guys can do a better job with so we have this to be of radius smaller, if I'm right, and that is your capital R. Now, case. Let's look at the small r is less than capital R. So what is the field? What does it tell? What do you think it will be? See, when the field lines are radiating outward, will there be any flux going inward? No, right? When this is a scenario, when this is 90 degree and all of that, it's going outward. There's no point of us talking about inward. But yeah, as a derivation, we have to talk about it, telling that as no charge is closed by the Gaussian sphere, right? So your flux will be equal to 0, and therefore E inside is 0 Newton per Coulomb. Does it make sense? Now, case if we are on the surface. So what will happen here? We'll make use of our Gaussian theorem. That it is Q by epsilon naught. Right? The flux is given by this particular formula. That's the general statement for flux. And this is by Gauss's theorem. So all of this has to be listed. Now, he is constant throughout. E here is constant and R parallel to area vector, and so we can tell theta is equal to 0 degree. Therefore, the LHS will be E integration of ds cos of 0 degree, and this is Q by epsilon naught. The charge, total charge is what? Total charge is not given. Total charge will be 4 pi r square into the charge density sigma. Right? We'll write the reason over here as Q is equal to density into area, and the area of the sphere is 4 pi r square. That you guys need not write. So your LHS is E, and the surface over here is again 4 pi r square. This is equal to 4 pi r square divided by epsilon naught rho. Okay, yes. Reason being the capital R and small r are one and the same, so I'm not even bothering with which variable I am using. So this and this will get cancelled, and this behaves as if it's independent of distance. Actually, it is. I mean, we are on the surface, right? Now the case of wherein small r is greater than r, that is a radius. In this case, the funda will change, right? We already written this formula. S EDS is equal to Q by epsilon naught. And here things will change, right? We have the same thing. Here he is constant and parallel to the area vector. And so theta is 0. And therefore we have E integration of ds cos of 0, which is equal to, here things will change. How will it change? Say we have the density into area of the sphere, not Gaussian sphere, the charged sphere, right? So here it would be 4 pi r square, and here it would be 4 pi capital R square. That's the difference. Agree, guys? And so a bit of rearrangement and stuff. Charge density capital R squared by small r square. Agree? Basically, in terms of unit and all of that, it depends on the density and your distance from the sphere. Actually, there's one more thing. I'm going to multiply and divide with 4 pi. Basically, I'll get back E is equal to rho pi 4 pi capital R square, denominator 4 pi. Oh, sorry, I missed out epsilon naught itself. Epsilon naught, epsilon naught, epsilon naught into R square. Okay, so 4 pi small r. Let me not take this. And let me keep this over here as well. In the numerator, what does it lead to? The numerator, it is nothing but the sphere. Sphere into the area of the sphere into density. What does it give? Total charge. That is what we wrote over here, is it not? I have written over here. So in the numerator, you have it to be q by, in the denominator, it is 4 pi epsilon naught r square. How does this look like? We have seen this somewhere, is it not? Yes, it looks like r. Correct. Your normal formula for your point charge. So whenever we are looking at a spherical structure with charge, from outside the sphere, it looks like as if there is no sphere, it is just a point charge. So the conclusion is the charged surface or spherical shell behaves like a point charge. That's it. Agree? So a very simple scenario, we have a sphere and we're looking at 3 different cases. We looked at 3 different cases. So case 1, case 2 and case 3. Inside though there is no charges, so there's nothing. Outside you got it as density by epsilon naught, if I'm right. Something, you guys can have a look and correct this if I'm wrong. And outside it took like a point charge. I mean this thing is point charge, not that. And the same funda, look into the pattern of the electrical field. Then the Gaussian surface turns out to be spherical, right? And then we have three different cases: less than r, greater than r, and where is that? Equal to r. Oh, it's here itself. Equal to r, right? Less than r, it has to be no charge. Equal to r, well, both the r's are same, so we get a very simple expression. Greater than r, we get a point charge expression. That's it. Easy to remember if you know the derivation. Okay, guys. Looks like a point charge. That is better. If I stand over here. Here, this is correct. This is correct. Here it is equal to 0 Newton per Coulomb. Okay.